Jupiter, a world of colossal storms, deadly radiation, and captivating beauty. A cosmic powerhouse whose mass is so immense that it exerts a measurable gravitational influence even on the Sun itself. In recent years, Jupiter has become one of the most intensely studied objects in our solar system. With 7 flybys, 2 orbiters, one of which is still operating today, and 2 additional missions already planned. There are so many questions waiting to be answered. What gives Jupiter its distinctive reddish coloration? What is this giant planet truly made of? What lies hidden beneath its thick, obscuring clouds? And what exactly is the Great Red Spot, the giant storm that has raged for centuries? Jupiter is not just another planet. It plays a vital role as a gravitational shield, helping protect the inner solar system. And now, it is time to dive deeper into its mysteries. Jupiter is the 5th planet from the Sun. It lies on the outer edge of the asteroid belt, positioned between the orbits of Mars and Saturn. Its average distance from the Sun is 778 million kilometers, or about 5.2 astronomical units. It takes roughly 12 Earth years to complete a single orbit around the Sun. The planet's axial tilt is very small, only about 3 degrees. This means it experiences very little seasonal variation, unlike Earth or Mars. And more similar to Saturn, Jupiter's radius at the equator is larger than at the poles, giving it a slightly flattened shape due to its rapid rotation. Jupiter is the largest planet in the solar system. Its mass is about 1,000th that of the Sun. That may not sound like much at first, but when you consider that the Sun contains 99.86% of all the mass in the solar system, the scale of Jupiter becomes truly extraordinary. When you begin to compare the numbers, the scale becomes almost surreal. Jupiter alone accounts for nearly all the remaining planetary mass in the solar system. Its mass is about 2.5 times greater than all the other planets combined. And this leads to something truly fascinating. The barycenter between Jupiter and the Sun, the shared center of mass they both orbit, actually lies above the surface of the Sun, at roughly 1.68 solar radii from the Sun's center. To understand this, we need to talk about barycenters. When we imagine something orbiting another object, we usually picture the smaller object simply circling the larger one. But in reality, both objects orbit a common center of mass. In most cases, this effect is so small that it can be ignored, like the International Space Station orbiting Earth, or even Mercury orbiting the Sun. The larger body barely moves. But Jupiter is different. Because of its enormous mass and its distance from the Sun, its gravitational influence is far from negligible. As Jupiter moves along its orbit, both it and the Sun perform a subtle gravitational dance around this shared center. And remarkably, that center lies just outside the Sun's surface. Imagine a simple example. Take a heavy object and a lighter object and attach them to opposite ends of a long stick. If you try to balance that stick, the center of mass will not be in the middle. It will shift closer to the heavier object. Now imagine the heavy object as the Sun, the lighter one as Jupiter, and the stick as gravity itself. That is how a barycenter works. Despite being the most massive planet in the solar system, Jupiter is not the densest. Its dominance comes from its sheer size. If Neptune were as large as Jupiter, it would actually be more massive. And if Jupiter were compressed down to the size of Earth, Earth would be more than 4 times as massive as it is now. But in reality, Jupiter's diameter is about 11 times that of Earth, and its total mass is roughly 318 times greater. And mass shapes gravity at the level where Jupiter's cloud tops define its visible surface. Gravity is about 2.5 times stronger than on Earth. This immense gravitational pull allows Jupiter to influence every planet in the solar system to some degree. It can tear apart asteroids, capture dozens of moons, at least 67 that we know of, and possibly many more. Some scientists believe that in the early solar system, Jupiter may have destroyed or scattered many forming planetary bodies, even preventing additional planets from emerging. One possible example is the region where the asteroid Vesta formed. There is also the long-term effect on Mercury. Jupiter's gravity subtly perturbs Mercury's already eccentric orbit, and over billions of years, this instability could eventually send Mercury spiraling into the Sun or eject it from the solar system entirely. And yet, Jupiter may also be a protector, acting like a cosmic vacuum cleaner. It can capture or deflect dangerous objects, such as long-period comets, or alter their trajectories just enough to send them out of the solar system. Without Jupiter, the inner planets, including Earth, might face far more frequent catastrophic impacts. Jupiter is the fifth planet from the Sun, about 5 times farther away than Earth. Even so, it is often the third brightest object in the night sky. After the Moon and Venus, at its brightest, it reaches a magnitude of -2.94, bright enough to cast faint shadows under dark skies. This makes it a perfect target for amateur astronomers. With modern consumer telescopes, even from a backyard, it is possible to observe its cloud bands and changing patterns. These iconic bands come from a surprisingly thin cloud layer, only about 50 kilometers thick. The clouds are composed largely of ammonia crystals, similar to those found on Saturn. But the vivid colors come from deeper within the planet. Chemical compounds rise upward from the interior, carried by powerful convection. These substances, known as chromophores, interact with ultraviolet light from the sun, producing the striking reds, browns, and creams that define Jupiter's appearance. This is a dynamic and ever-changing system. The face of Jupiter can shift dramatically over time. Bands can widen or narrow. Storms can appear and vanish. But their positions along latitude remain consistent enough that scientists can map and track them. Where these bands meet, turbulence intensifius. Massive storms are born from these interactions. And at the heart of it all lies the most famous storm in the solar system, the Great Red Spot. This storm is enormous. It is so large that the entire diameter of Earth could fit comfortably inside it. It has existed for as long as we have been observing Jupiter. First recorded in the 17th century, and it may well be a permanent feature of the planet. Yet, interestingly, over time, it has been shrinking. The reason behind its deep red color is still not fully understood. The hue can vary dramatically, shifting from a rich brick red to an almost pale white. One of the leading theories suggests that chemical compounds are broken apart by ultraviolet light from the sun, in much the same way as the processes that color the rest of Jupiter's atmosphere. The storm itself rises higher in the atmosphere than the surrounding clouds, allowing it to interact more directly with sunlight. This could explain why its color often appears more intense than anything around it. But Jupiter does not host just one remarkable storm. Another feature, known as Red Spot Junior, formed when 3 separate storms merged between the late 1990s and early 2000s. It has so far avoided being consumed by its much larger neighbor and has become a prominent feature in its own right. If it continues to avoid destructive interactions, it could persist for several hundred more years. Unlike other storms that have passed through the Great Red Spot and disappeared. So, what is Jupiter actually made of? Much like Saturn, beneath its thick atmosphere lies layers of gas, then liquid, and eventually metallic hydrogen. As you descend deeper into the planet, the pressure increases to unimaginable levels. Under such extreme conditions, hydrogen begins to behave like a metal. Beneath this layer, scientists believe there may be an icy or rocky core. Because we cannot recreate these immense pressures here on Earth, the exact properties of these materials remain uncertain. Current estimates suggest that Jupiter is composed of roughly 90% hydrogen and about 10% helium, with trace amounts of methane, ammonia, and other compounds. Jupiter also rotates incredibly fast, faster than any other planet in the solar system. It completes a full rotation in about 10 hours. However, because it is not a solid body, different regions rotate at slightly different speeds, with the poles taking a few minutes longer than the equator. It is natural to wonder why Jupiter is not a star. After all, it is massive and made primarily of hydrogen. But stars do not ignite through simple combustion. There is very little oxygen on Jupiter. And even more importantly, stars generate energy through nuclear fusion, not chemical burning. For fusion to begin, the pressure and temperature at the core must reach extreme levels. Current models suggest that Jupiter would need to be around 75 times more massive to become a true star. Interestingly, its size is not too far from the smallest known red dwarf stars. But its mass simply is not sufficient. Jupiter also has rings, though they are far less dramatic than those of Saturn. There are 4 main ring components. The primary ring is thin and relatively bright, while the others are broader but extremely faint. The main ring spans about 6,000 kilometers in width and contains a subtle feature known as a notch. Another striking feature of Jupiter is its powerful magnetosphere. It is about 14 times stronger than Earth's, generated by the motion of liquid metallic hydrogen within its interior. This makes it the strongest planetary magnetosphere in the solar system, second only to the influence of the Sun. This magnetic field channels charged particles from the solar wind toward the poles, producing brilliant auroras. It also envelops Jupiter's largest moons, shielding them from direct exposure to the solar wind. However, this protection comes with a cost. Jupiter is surrounded by an intense radiation belt. Any spacecraft passing through this region faces extreme conditions. The moon Io, which orbits closest to Jupiter, travels directly through the heart of this radiation zone, receiving enormous doses of radiation every single day. To put that into perspective, the radiation levels on Io would be fatal to a human within just a few hours. It is one of the most hostile environments in the solar system. Jupiter has at least 67 known moons, most of them small, many less than 10 kilometers across. But the 4 largest, known as the Galilean moons, are among the most fascinating worlds we have ever studied. These are Io, Europa, Ganymede, and Callisto. Each one is unique. Ganymede, in particular, is the largest moon in the entire solar system, even larger than the planet Mercury. And if you observe Jupiter in infrared light, what you see is something even more extraordinary. A world of immense energy, shifting heat, and powerful forces, revealing the true scale and intensity of this giant planet. That tiny dark mark near the bottom of the planet is the scar of an impact. An object from deep space collided with Jupiter, leaving behind a visible imprint on its atmosphere. If that same object had struck Earth, it could have brought an end to life as we know it. In moments like this, it becomes clear. Jupiter is not just a giant planet. In many ways, it is a silent guardian of the solar system. Jupiter protects, absorbs, deflects. It takes the hits that might otherwise reach the inner worlds. And because of that, Its presence is not just beautiful, it is essential. Now let's take a step further. Most of us are familiar with how the planets look in visible light. Saturn with its pale golden glow, Jupiter with its swirling red bands and layered clouds, Neptune with its deep, dark blue color. But visible light is only a tiny fraction of the story. Planets do not just reflect light we can see. They also emit and interact with wavelengths beyond human vision, such as infrared and ultraviolet. And in many cases, these hidden wavelengths reveal far more than what our eyes ever could. Some features that are completely invisible in visible light become strikingly clear in infrared. Others disappear entirely. If we want to truly understand what a planet is made of, how it behaves, and what processes shape it, we have to look across the entire electromagnetic spectrum. When we observe Jupiter in natural light, it appears as a stunning world of layered clouds and flowing bands. These are not water clouds like those on Earth. They are composed primarily of ammonia ice. If you look closely, you can begin to sense depth within the atmosphere. The darker, narrow regions are actually shadows cast by taller, brighter cloud structures. Higher altitude clouds tend to appear lighter, almost pure white, especially in the highest regions where they rise above the surrounding layers. The colors we see are believed to come from chemical compounds rising up from deep within Jupiter. As they reach higher altitudes, they are exposed to ultraviolet radiation from the sun, which alters their composition and darkens them before they eventually sink back down again. But here is the limitation. Jupiter's cloud layer is opaque. We cannot see through it using visible light alone. If that were the only tool we had, most of the planet would remain hidden from us. Fortunately, we are not limited to what our eyes can see. When we observe Jupiter in certain infrared wavelengths, an entirely new world is revealed. One of the most striking views comes from observations at a wavelength of 4.68 microns. At this wavelength, we are no longer seeing reflected sunlight. We are seeing heat. And what we discover is surprising. The darker reddish bands, which appear subdued in visible light, become the brightest regions in infrared. This is because Jupiter emits more heat than it receives from the sun. The planet is slowly contracting, and this process generates internal heat. That heat escapes through the atmosphere, most easily in regions where the cloud layer is thinner. This is why features like the Great Red Spot, which appear bright in visible light, often appear darker in infrared images. The thick clouds trap heat, preventing it from escaping as easily. The Juno spacecraft has taken this even further. By observing Jupiter's poles in infrared, scientists have been able to construct three-dimensional maps of the Vishal vortices that dominate these regions. At the North Pole, there are 9 persistent cyclones, 8 arranged around a central storm, forming a stable geometric pattern that continues to rotate over time. In this infrared view, the lowest altitude regions glow brightest, revealing where heat is escaping. Unlike visible light, infrared observations are not blocked as easily by haze or shadow. This allows scientists to see deeper into the structure of the atmosphere. Even then, temperatures remain extremely low by Earth standards. The brighter regions may reach around -3 degrees Celsius, while higher altitude areas can drop to around -83 degrees Celsius. And because this heat comes from Jupiter itself, these observations can be made both day and night. Infrared observations also allow scientists to detect storms before they become visible. Deep within the atmosphere, warmer regions can signal the early formation of new storms long before they emerge through the cloud tops. And this same approach reveals something extraordinary on Jupiter's volcanic moon, Io. On its night side, the surface glows with heat from active volcanoes. entire regions light up, making it possible to track eruptions and discover new volcanic activity. It is a world of constant change, is violent, Kramen, extreme, and endlessly fascinating. Europa, another of Jupiter's great moons, tells a different story. Using specific infrared wavelengths, scientists can detect the presence of water ice on its surface. At around 1.5 microns, the deepest blue regions in the data correspond to the purest ice, while other colors indicate mixtures with different minerals. This technique is known as spectroscopy. Instead of seeing a simple image, scientists are reading data encoded in light itself. When light reflects off a surface, certain wavelengths are absorbed depending on the molecules present. By analyzing which wavelengths are missing, scientists can determine what substances are there without ever touching the surface. In another view, scientists can map the presence of sulfuric acid on Europa. Brighter regions in these datasets indicate higher concentrations, often found along surface fractures. These may originate from the ocean beneath the icy crust, or from interactions with charged particles in Jupiter's radiation environment. And slowly, piece by piece, across wavelengths we cannot see, Jupiter and its moons begin to reveal themselves, not just as distant points of light, but as dynamic, complex worlds shaped by forces far beyond our everyday experience. Europa is constantly bombarded by sulfur ions, and remarkably, much of that sulfur likely originates from the volcanic eruptions on Io, Jupiter's most active moon. Material blasted into space from Io does not simply disappear. It becomes part of a complex system, interacting with Jupiter's magnetic field and eventually reaching other moons. If we turn our attention to Callisto, infrared data reveals something even more intriguing. When scientists overlay infrared observations onto visible light images, entirely new patterns emerge. In these maps, red tones indicate regions rich in water ice, while blue tones represent areas with less. One of the highest resolution infrared images we have of a body in the Jovian system focuses on a region only about 200 kilometers across. And within that small area, a fascinating structure appears. There is a concentration of water ice inside the crater, then a surrounding ring where water is almost absent, followed again by icy material spreading outward in a ray-like pattern. The icy regions likely formed when the impact exposed material buried beneath the surface, but the ring between the crater and the outer debris remains something of a mystery. It may be that the ejected icy material did not begin falling back to the surface until it reached a certain distance. Whatever the explanation, this pattern suggests that non-icy material forms only a thin layer on the surface of Callisto. Now, if we look at Jupiter itself through different infrared wavelengths, the planet transforms again. At wavelengths around 1.61 and 2.73 microns, we can still see the cloud deck in a way that resembles visible light. But at around 2.17 microns, something changes. This is an absorption band for hydrogen. Because Jupiter is composed primarily of hydrogen, the atmosphere becomes opaque at this wavelength. Most of the familiar features disappear, and only the highest altitude clouds remain visible, the ones that rise above the dense hydrogen layers below. At around 3 microns, methane and ammonia begin to dominate the absorption. At roughly 5 microns, we once again see a heat map, revealing where energy is escaping from the planet's interior. And when scientists combine these different wavelengths into a single false color image, they are not creating art. They are building a map of physical processes, assigning colors to represent data that would otherwise be invisible. Ultraviolet observations add yet another layer of understanding. While ultraviolet is not always the most useful tool in planetary studies, It played a crucial role in tracking the aftermath of a historic event. The impact of comet Shoemaker-Levy 9 in the year 1994. The dust from the impact absorbed ultraviolet light, allowing scientists to track wind patterns in Jupiter's stratosphere as the debris spread and evolved. But ultraviolet light also reveals something else: Jupiter's auroras. These auroras are vastly more powerful than those on Earth. They are not occasional displays. They are permanent features. Driven by Jupiter's immense magnetic field, charged particles are funneled into the upper atmosphere, where they collide with gases and release energy in the form of light. The Hubble Space Telescope has observed these auroras in ultraviolet for years. But some of the most detailed views have come from the Juno spacecraft, which passes directly over Jupiter's poles. These observations show how deeply the auroras are connected to Jupiter's magnetic environment and even to its moons, through streams of charged particles known as flux tubes. When we put all of this together, a clearer picture begins to form. Spectroscopy, absorption, and emission across different wavelengths allow us to identify molecules, map heat, and observe interactions between a planet and its environment. It is through this broader view of light that Jupiter transforms from a distant world into a dynamic system we can begin to understand. And then, in July of 1994, humanity witnessed something extraordinary. Comet Shoemaker-Levy 9 collided with Jupiter, fragment by fragment, over the course of several days. The comet slammed into the planet with unimaginable force. The energy released was equivalent to hundreds of millions of nuclear explosions. Plumes of debris rose thousands of kilometers above the cloud tops. Despite Jupiter's immense gravity, temperatures at the moment of impact soared to tens of thousands of degrees Celsius. The comet itself was traveling at over 216,000 kilometers per hour, and its largest fragment stretched about 2 kilometers across. The impacts left scars in Jupiter's atmosphere that were visible for months, darker and larger than the Great Red Spot itself. Events like this are not unique in the history of the solar system. Earth itself bears the marks of ancient impacts, including the one that likely led to the extinction of the dinosaurs at the end of the Cretaceous period. But witnessing such an event in real time is extraordinarily rare, and it raises an unsettling question. If Jupiter had not been there, if that comet had taken a different path, would we have been the ones watching the sky change forever? What did this event teach us about Jupiter and about planetary collisions? The story begins in the year 1993, when astronomers Caroline Shoemaker, Eugene Shoemaker, and David Levy were conducting observations at the Palomar Observatory in California. During their research, they discovered something unusual, a comet that was not orbiting the Sun in the typical way, but instead had been captured by Jupiter's immense gravitational pull. This was what we call a periodic comet, meaning it completes an orbit in less than 200 years. Most comets in the solar system follow long paths around the Sun, but Jupiter is so massive, far larger than any other planet, that it can trap passing objects within its gravitational influence. In fact, many of Jupiter's irregular moons are believed to be captured asteroids and comets that have lost their volatile materials over time. But this comet stood out for several reasons. First, it was enormous. Scientists estimated that impacts from objects of this size might occur only once every 6,000 years. Second, it was fragmented. Instead of a single solid body, it had already been torn into multiple pieces, most likely by Jupiter's tidal forces during a previous close encounter. And then there was its orbit, highly eccentric, almost extreme. Orbital eccentricity measures how stretched an orbit is, where 0 represents a perfect circle, and values approaching 1 indicate a highly elongated path. This comet's eccentricity was greater than 0.998. In other words, Its trajectory was nearly as extreme as physically possible while still remaining bound. Almost immediately, astronomers realized that a collision with Jupiter was not just possible, it was likely. As more precise data came in, that possibility became certainty. The impact would occur in July of 1994, and soon, the entire world was watching, waiting for what would become one of the most extraordinary astronomical events ever observed. Observatories across the globe began tracking the comet's fragments. The Keck Observatory, the Rosat X-ray Telescope, and the Hubble Space Telescope all focused their instruments on Jupiter. Every movement was monitored, every fragment mapped. But when the first fragment was set to collide on July 16, 1994, it seemed that the worst-case scenario had arrived. The impact would occur on the far side of Jupiter, hidden from Earth. Even the most powerful telescopes on our planet would not be able to see the initial moment of collision. For scientists, this could have been a devastating loss, a once-in-a-lifetime event, happening just out of sight. But space had one more surprise waiting. By remarkable coincidence, NASA's Galileo spacecraft, launched in 1989, was already on its way to Jupiter. At that moment, it was perfectly positioned to observe the impact directly. It became humanity's eyes in space, capturing data that Earth-based instruments could not. And Galileo was not alone. The Ulysses spacecraft, originally launched to study the Sun, also turned its instruments toward Jupiter. Even Voyager 2, located 44 astronomical units away, was reprogrammed to detect radio emissions from the impact using its ultraviolet spectrometer. For a brief moment, spacecraft across the solar system paused their own missions and worked together, all focused on a single event, a cosmic collision unfolding in real time. And as the first fragment approached Jupiter, the world held its breath. Galileo watched as a massive fireball erupted from Jupiter's atmosphere, reaching temperatures of around 24,000 degrees Celsius. The plume rose nearly 3,000 kilometers into space, a scale comparable to the entire length of Australia from north to south. This was something scientists had not expected, a fireball of that magnitude, in the aftermath of such an impact, was beyond predictions. Minutes later, the ejected debris began to fall back toward the planet, burning again as it re-entered the atmosphere. For a brief moment, Jupiter became a raging furnace. Then, as the planet rotated, the impact site slowly came into view from Earth. Telescopes like Hubble revealed a massive dark scar imprinted on Jupiter's clouds. Jupiter rotates incredibly fast. A full day lasts only about 10 hours. And larger planets often spin faster than smaller ones. The energy from the impact sent shock waves rippling through Jupiter's dense atmosphere at speeds of over 4,400 meters per second. And that was only the beginning. Over the course of 6 days, from July 16th to July 22nd, the fragments of the comet continued to strike the planet. The most powerful impact occurred on July 18th. When fragment G collided with Jupiter, that single impact released energy hundreds of times greater than the entire nuclear arsenal of Earth, leaving behind a dark scar roughly the size of our planet. But as dramatic as the impacts were, the aftermath proved just as valuable. The debris clouds gave scientists a rare window into Jupiter's atmosphere and its internal dynamics. For the first time, spectroscopic measurements revealed material from beneath the cloud tops. They detected diatomic sulfur, carbon disulfide, and heavier elements such as silicon, iron, and magnesium. And unexpectedly, they also found significant amounts of water. This discovery raised new questions that scientists are still trying to answer today. including where that water is stored within Jupiter's atmosphere. Perhaps the most unsettling realization, however, was this. Collisions of this scale are not just events of the distant past. They can still happen. Before this event, many scientists believed that large impacts were far more common in the early solar system and extremely rare today. But Shoemaker Levy 9 proved that devastating collisions are still possible. The question is no longer whether they can happen, but how often. We have only had the technology to observe such events for a few decades. It is entirely possible that impacts like this occur more frequently than we realize. If a comet of similar size were to strike Earth, the consequences would be catastrophic. Most life on the planet would not survive. The event left a deep impression on the scientific community and the public alike. It became a turning point. Before this, the concept of planetary defense did not truly exist. Afterward, it became a priority. Space agencies began systematically tracking near-Earth objects, identifying asteroids and comets that could pose a threat. The goal was to detect the vast majority of objects larger than 1 kilometer, and that objective has largely been achieved. Now, efforts continue to track even smaller bodies, down to around 140 meters in size. But there is another perspective to consider. Jupiter itself may be one of the reasons Earth has remained relatively safe. Because of its enormous mass and gravitational reach, Jupiter attracts and captures far more comets than Earth ever could. Some estimates suggest it experiences thousands of times more comet impacts. In that sense, Jupiter may act as a cosmic vacuum cleaner, drawing in dangerous objects before they can reach the inner solar system. This idea is part of what is known as the rare Earth hypothesis. The notion that Earth's ability to support complex life depends on a unique combination of conditions, including the presence of a giant planet like Jupiter acting as a shield. Not all scientists agree with this idea, and much remains uncertain. But what is certain is this. The collision of Shoemaker Levy 9 with Jupiter transformed our understanding of planetary impacts. It was one of the most powerful and spectacular events ever witnessed in the solar system. A reminder of both the violence and the beauty that exist on a cosmic scale. And beyond Jupiter itself, there are other worlds waiting to be explored. Smaller, less well known, but no less fascinating. Among them are the 4 largest moons of Jupiter, known as the Galilean moons. Despite orbiting the same planet, they are dramatically different from one another. One is a world of constant volcanic activity. Another may hide an ocean beneath its icy surface. One of the most promising places to search for life. One is the largest moon in the solar system, and another is an ancient world, covered in scars that date back to the earliest days of planetary formation. These moons were first observed in the year 1610 by Galileo, and they remain some of the most intriguing objects we have ever studied. From closest to farthest, they are Io, Europa, Ganymede, and Callisto. Io orbits incredibly close to Jupiter. At a distance of about 350,000 kilometers above the cloud tops, from its surface, Jupiter would appear enormous in the sky, about 39 times larger than our moon appears from Earth. Io completes an orbit around Jupiter in just over 42 hours. And because of its proximity, the tidal forces acting on it are extreme. The surface of Io is constantly flexing, with tidal bulges reaching up to 100 meters in height. This is similar to the tides on Earth caused by our moon, but on a vastly greater scale. On Earth, ocean tides typically rise and fall by only a few meters. On Io, the forces are far more intense. Because of gravitational interactions with Jupiter and the other large moons, Io's orbit remains slightly elliptical. This means the tidal forces never fully settle. The moon is continuously being stretched and squeezed, generating enormous internal heat. A day on Io is the same as its orbital period. It is tidally locked. Just like our moon, one side always faces Jupiter, while the other remains turned away. And in that constant tension between gravity and motion, Io becomes one of the most extreme and active worlds in the entire solar system. Io is a large moon. Although it is the second smallest of the Galilean moons, it is comparable in size to Earth's moon and has a similar density, meaning its surface gravity is also quite similar. But interestingly, Io has the highest density of any moon in the entire solar system. One of many features that set it apart. Unlike most large moons, which are composed largely of water ice and silicate, Io is made primarily of silicate rock and iron, much like the terrestrial planets and our own moon. In fact, Io contains less water than almost any other known body in the solar system. Its interior likely consists of an iron or iron sulfide core, surrounded by a silicate-rich mantle and crust. The core is not believed to be convective, as no global magnetosphere has been detected. However, the mantle near the crust is thought to be partially molten and at least 50 kilometers thick. This is the source of Io's extreme volcanic activity. And this brings us to what makes Io truly extraordinary. Its surface is covered with hundreds of massive volcanoes. Before the 1970s, very little was known about Io. Early telescopic observations suggested it lacked water and might have a surface rich in sulfur. The first spacecraft to provide closer insight was Pioneer 11. Although its images were limited in quality, it revealed that Io was composed of rock rather than ice and possessed a thin atmosphere. Pioneer 10 was also intended to capture close-up images, but its instruments were overwhelmed by Jupiter's radiation. The radiation environment it encountered was about 10,000 times stronger than the maximum levels typically found around Earth. The real breakthrough came in 1979, when Voyager 1 and Voyager 2 flew past Jupiter. Voyager 1 passed within about 20,000 kilometers of Io, capturing detailed images of its surface. What it revealed was astonishing. A landscape filled with vivid colors, completely lacking in impact craters. Instead, there were towering mountains higher than Mount Everest, Vishal volcanic pits stretching hundreds of kilometers across, and vast flows of lava. Most importantly, Voyager 1 observed plumes rising from the surface. This confirmed that Io is volcanically active. It remains the first and only place beyond Earth where active volcanism has been directly observed. Voyager 1 also showed that Io's surface is coated in various forms of sulfur frost. These compounds are responsible for the moon's striking colors. The atmosphere itself is dominated by sulfur-based gases. Voyager 2 observed Io a few months later, from a much greater distance of about 1 million kilometers. Even so, it detected several of the same volcanic plumes, suggesting that these eruptions had remained active over time. The next major leap came with the Galileo spacecraft, which arrived at Jupiter in the mid-1990s. Although it was not specifically designed to study Io, it captured some of the highest resolution images we have of the Moon. Despite technical issues that limited its full capability, Galileo confirmed ongoing volcanic activity across Io's surface. It observed eruptions of sulfur and silicate magma, similar in some ways to volcanic processes on Earth, but with key differences. Io's magma is also rich in magnesium, indicating extremely high temperatures. The surface of Io is one of the most colorful in the solar system. Yellow regions are dominated by sulfur. White areas are covered in fresh sulfur dioxide frost. Near the poles, radiation alters the sulfur, giving those regions a deeper reddish tone. In other areas, red deposits mark the locations where volcanic plumes have erupted and settled back onto the surface. One of the most prominent volcanic features is Pele. Although it was inactive during the Galileo mission, Voyager 1 captured an enormous plume rising from it. That plume reached about 300 kilometers in height and spread over 1,200 kilometers wide, comparable in scale to the size of Alaska. But Io's volcanoes are not like those on Earth. Instead of the classic cone-shaped structures with central craters, many volcanic regions on Io form vast lava lakes surrounded by high walls. One of the most famous is Loki, the largest volcanic depression on Io, spanning about 200 kilometers in diameter. These lava lakes are directly connected to reservoirs of molten rock below the surface. Often, a thin crust forms on top, but this crust is unstable. Periodically, it collapses back into the molten lake beneath. When that happens, Loki can suddenly release enormous amounts of heat, sometimes producing up to 10 times its normal energy output. Io is not just active. It is alive with constant motion, a world shaped by relentless tidal forces, where the ground itself is never truly still. This process can be seen clearly in one of Io's major volcanic regions, Tvashtar. Under normal conditions, the surface appears relatively stable, but in certain moments, the crust above the lava lake begins to collapse, sinking back into the molten interior. In some images, the energy released is so intense that the camera sensors become overwhelmed, registering nothing but pure white where the lava curtain erupts. In the year 2007, the New Horizons spacecraft used Jupiter as a gravity assist on its journey toward Pluto. During its flyby, it turned its instruments toward Io. What it captured was extraordinary. Tvashtar was in full eruption, with a massive plume rising hundreds of kilometers above the surface. Smaller eruptions could also be seen scattered across the moon. It remains one of the most striking scenes ever observed in space. Despite the generally flat appearance of its volcanic plains, Io also hosts some extremely tall mountains. The tallest reach heights of up to 18 kilometers, unlike mountain ranges on Earth. These peaks often stand alone, isolated structures rising from the surface. Most are not volcanoes, yet lava lakes are frequently found nearby, suggesting deep fractures in the crust beneath them. Another fascinating aspect of Io is its interaction with Jupiter's magnetic field. Jupiter possesses an enormous and powerful magnetosphere, and Io orbits within one of its most intense regions. As material from Io's thin atmosphere and volcanic eruptions escapes into space, it forms a vast neutral cloud that follows the Moon's orbit and extends far beyond it. Surrounding Jupiter is another structure known as a plasma torus, a donut-shaped ring of ionized particles that rotates along with the planet's magnetic field. This torus moves much faster than Io itself, traveling at about 70 kilometers per second, while Io orbits at roughly 17 kilometers per second. As Io passes through this environment, particles from the torus collide with those in the neutral cloud, energizing them and turning them into charged particles. These newly ionized particles are then captured by Jupiter's magnetic field, feeding back into the plasma torus at a rate of about 1 ton of material every second. This constant flow helps sustain and expand Jupiter's already enormous magnetosphere. If it were visible from Earth, Jupiter's magnetic field would appear as large as the Moon in our sky. The interaction does not stop there. Magnetic field lines connecting Io to Jupiter create an electrical current known as the Io flux tube. This current channels energy directly into Jupiter's upper atmosphere, producing a bright auroral footprint near the poles. Auroras also occur on Io itself, unlike Earth, where they are mostly confined to the poles. Io's auroras can appear across its surface. Their colors reveal the elements involved. Green indicates sodium, red corresponds to oxygen, and blue comes from sulfur. And then, Beyond Io, we arrive at one of the most intriguing worlds in the entire solar system, Europa. Europa is the second of the Galilean moons and the smallest of the four. Yet it is still the sixth largest moon in the solar system, with a diameter of about 3,000 kilometers. It orbits Jupiter once every 3.5 days. What makes Europa especially interesting is its orbital relationship with Io and Ganymede. These three moons are locked in a 4:2:1 orbital resonance. This gravitational interaction ensures that Europa's orbit is never perfectly circular. Instead, it remains slightly elliptical. As Europa moves closer to and farther from Jupiter, the gravitational pull it experiences changes. This creates powerful tidal forces that flex and stretch the moon's icy surface. These forces are not just superficial. They shape the entire structure of the moon and drive activity beneath the surface. Europa's surface is composed primarily of water ice, giving it a smooth and reflective appearance. It is marked by long, continuous fractures known as lineae. These features are typically 1 to 2 kilometers wide, but can stretch for thousands of kilometers across the surface. The exact mechanism behind their formation is still not fully understood, but the leading theory suggests that tidal forces pull the crust apart, allowing warmer material from below to rise up and fill the gaps. Similar to processes seen at mid-ocean ridges on Earth, scattered across the surface are small, dark features known as lenticular. These are roughly 10 kilometers across and are thought to form when warmer. Less dense material rises toward the surface, pushing the crust upward or breaking through it entirely. In some regions, this process creates chaotic terrain, areas where the surface appears broken, jumbled, and uneven, surrounded by smoother ice. These regions may hold important clues about what lies beneath Europa's surface. Data also suggests that Europa's equatorial regions may be covered in icy spikes, known as penitentes. These formations can reach heights of up to 15 meters and are thought to form under direct sunlight, similar to structures found in high-altitude regions on Earth, though much larger. Despite being nearly as old as the solar system itself, Europa has very few impact craters. Fewer than 50 large craters have been identified, compared to thousands on Earth's moon. This indicates that Europa's surface is constantly being renewed. Estimates suggest that the surface is between 30 million and 180 million years old, extremely young in geological terms. It is also the smoothest known solid surface in the solar system, with a high reflectivity, or albedo, of about 0.64. Europa's albedo makes it about 5 times brighter than our moon. But beneath that brightness lies an extremely hostile world. Its surface is constantly bombarded by intense radiation from Jupiter, reaching levels of roughly 5,400 millisieverts per day, enough to kill a human in less than a single day. The reddish-brown streaks across its fractured surface are believed to be salts and sulfur compounds mixed with water ice and chemically altered by this relentless radiation. A recent study from JPL suggests that Europa may even glow in the dark. Energetic ions from Jupiter penetrate the surface, exciting molecules beneath the ice and causing them to release energy as faint visible light. Unfortunately, we cannot observe Europa's night side from Earth, because our position always keeps us between it and the Sun. So confirming this phenomenon will require future missions. Radiation also shapes Europa's atmosphere. It is extremely thin and composed mainly of oxygen. But unlike Earth, this oxygen is not produced by life. Instead, it forms through radiolysis, where radiation breaks apart water ice into hydrogen and oxygen. The lighter hydrogen escapes into space, while the heavier oxygen remains, forming a tenuous atmosphere. Some of these particles create a vast cloud that follows Europa along its orbit around Jupiter. In 2012, the Hubble Space Telescope detected plumes of water vapor erupting from Europa's south pole, rising up to about 200 kilometers above the surface. In 2018, scientists reanalyzed old Galileo data and found additional evidence supporting these plumes. Studying them could allow us to understand what lies beneath Europa's icy shell without ever landing on it. Beneath that frozen crust, scientists believe there is a global ocean between a rocky mantle and an outer ice layer. Evidence for this hidden ocean first came from the Voyager mission in 1979 and later from Galileo in the late 1990s. These missions observed changes in Europa's magnetic field that can only be explained by the presence of a conductive liquid beneath the surface. Europa's crust also appears to rotate at an angle of about 80 degrees, something that would not be possible if it were rigidly attached to the mantle, suggesting that the icy shell floats above a liquid ocean and slowly shifts over time. It is estimated that this crust completes a full rotation relative to the interior roughly once every 12,000 years. This shifting explains the chaotic network of cracks across the surface, as tidal forces from Jupiter continuously flex the Moon. Europa orbits at a distance of about 780 million kilometers from the Sun, making sunlight there about 25 times weaker than on Earth. As a result, surface temperatures average around -60 degrees Celsius at the equator and drop to about -220 degrees at the poles, keeping the ice as hard as granite. Despite this cold, tidal forces from Jupiter generate heat inside Europa, allowing a subsurface ocean to remain liquid. This ocean likely lies beneath a crust only 15 to 25 kilometers thick and may extend down to depths of 60 to 150 kilometers. Although Europa is only about a quarter the diameter of Earth, it may contain twice as much water as all of Earth's oceans combined. What makes this ocean especially intriguing is that it may be in contact with Europa's rocky mantle, creating conditions similar to those where life exists on Earth. Scientists believe life requires water, energy, and minerals, and Europa appears to have all three. There is strong evidence that chemical reactions occur within this ocean and that geothermal activity may exist on its floor, potentially supporting entire ecosystems far from sunlight. For this reason, Europa is considered one of the most promising places to search for life beyond Earth. NASA's Europa Clipper mission is expected to reach the Moon by the end of the decade and perform dozens of close flybys, while the European Space Agency's Juno mission will study Jupiter and its icy moons in detail. These missions aim to analyze Europa's plumes, infer our days and atmosphere, bringing us closer to answering the most profound question of all: whether life exists beyond our planet. And then there is Ganymede, the largest moon in the solar system and home to what may be the largest ocean of all, with a diameter of over 5,200 kilometers. It is even larger than Mercury in size, though much less dense due to its high water content. Beneath its thick ice crust, which may extend about 150 kilometers deep, lies a vast ocean, possibly reaching depths of around 100 kilometers, containing more water than all of Earth's oceans combined. Ganymede is composed of roughly half rock and half water, giving it a much lower density than Mercury. It even has a thin oxygen atmosphere, though far too weak to support life as we know it. However, the immense depth of its ocean may actually prevent life from forming, as extreme pressure at the bottom could compress water into high-pressure ice, cutting off contact between the ocean and the rocky core, where essential minerals would normally be supplied. Europa, by contrast, remains the stronger candidate for life. But if Ganymede's ocean is salty, models suggest it may contain multiple layers separated by ice, and the deepest layer could still interact with the core. If that is true, then even this distant icy giant may not be entirely lifeless. And somewhere beneath these frozen surfaces, in the silent darkness far from the sun, entire hidden worlds may be waiting, untouched, unseen, and still holding answers we have only just begun to ask. But beneath Ganymede's layers of ice and water lies something far more surprising. Something scientists still cannot fully explain. Somehow, Ganymede is generating its own magnetic field. This discovery was first made in 1996 when the Galileo spacecraft performed a series of flybys and detected clear signs of magnetism, most notably through the presence of auroras in its thin atmosphere. Even more intriguingly, observations from the Hubble Space Telescope showed that these auroras did not wobble as much as expected, suggesting the influence of a conductive, salty ocean beneath the surface interacting with the magnetic environment. A magnetic field is an incredibly important feature because it can shield a world from harmful radiation, just as Earth's field protects life on our planet. However, Ganymede's field is not strong enough to fully protect it, as it still sits within Jupiter's immense magnetic field and radiation belts. The surface radiation levels remain high, reaching several rem per day, enough to make a human severely ill or even fatal within a couple of months. Though still less extreme than some of the inner moons, the real mystery is why this magnetic field exists at all. On Earth, the magnetic field is generated by convection within a molten core, where moving electrons create a dynamo effect. But Ganymede is smaller and less dense, and scientists believe its core should have cooled and solidified long ago, which would prevent such motion. No other moon in the entire solar system has a global magnetic field like this, making Ganymede uniquely puzzling. One possible explanation lies in tidal heating. Ganymede orbits Jupiter roughly once every 7 days in a slightly eccentric path, meaning its distance from Jupiter constantly changes. As it moves closer and farther away, Jupiter's gravity stretches and compresses the moon over and over again. This repeated flexing generates internal friction and heat, similar to how a material warms up when stretched and kneaded repeatedly. On a planetary scale, this process can produce significant internal energy. This effect is further amplified by an orbital resonance with Europa and Io. For every orbit Ganymede completes, Europa orbits twice and Io orbits 4 times, creating a precise gravitational rhythm that constantly pulls on Ganymede and adds to the stress within its interior. This continuous energy input may be enough to keep part of its core partially molten, allowing a magnetic field to persist. Ganymede's surface itself reflects a complex history shaped by these forces. About 1/3 of the surface consists of dark, heavily cratered regions that are much older, while the remaining 2/3 are brighter areas marked by long ridges and grooves that stretch for thousands of kilometers and rise hundreds of meters high. These features likely formed during periods of intense internal activity, possibly driven by tidal forces reshaping the crust. By studying the locations of auroras within Ganymede's atmosphere, scientists have even been able to confirm the presence of a subsurface ocean without ever landing there. The interaction between the magnetic field and this hidden ocean reveals clues about its composition and structure. Future missions, such as the JUICE spacecraft, are expected to explore this system in more detail and may finally provide answers to these long-standing questions. And then there is Callisto. Often overlooked, yet far from uninteresting, it is the 3rd largest moon in the solar system, slightly smaller than Mercury, but with only about 1/3 of its mass, making it far less dense. It orbits Jupiter at a much greater distance than the other Galilean moons, taking around 17 Earth days to complete one orbit, and remains tidally locked so that the same side always faces Jupiter. Callisto has an extremely thin atmosphere composed mainly of carbon dioxide, with possible traces of oxygen. However, this atmosphere is so sparse that its particles rarely collide, and in theory it should escape into space relatively quickly. Scientists believe it is continuously replenished by the sublimation of surface ice, maintaining a delicate balance over time. What makes Callisto truly remarkable is its surface. It is one of the oldest and most heavily cratered landscapes in the solar system, estimated to be over 4 billion years old. Unlike Earth or even Europa and Io, Callisto shows almost no signs of geological activity. There are no tectonic plates, no volcanism, and virtually no processes that reshape its surface. As a result, impact craters have accumulated over billions of years, overlapping to the point of near saturation. Because it lacks strong tidal forces, Callisto has remained geologically inactive, preserving its ancient appearance. It also lacks significant mountains, likely because its surface formed early as a frozen ocean world and has remained largely unchanged ever since. Among its most striking features are enormous impact structures such as Asgard, spanning about 1,600 kilometers, and Valhalla, the largest multi-ring crater in the solar system, stretching roughly 3,800 kilometers across. And in that frozen, cratered silence, Callisto stands as a time capsule of the early solar system, a world untouched by change, quietly holding the history of billions of years in every scar across its surface. It is these craters that give Callisto its uniquely textured appearance, with massive multi-ring structures unlike anything else in the solar system. These impacts were so powerful that they may have completely pierced through the moon's thin crust before refreezing, leaving behind the bright central regions we see today. When you zoom in on these areas, you notice a mottled pattern, a striking contrast between bright knobs and darker plains, suggesting that these surfaces are younger and likely formed from refrozen material, possibly billions of years more recent than the surrounding terrain. The concentric rings themselves are thought to be fractures in the crust, created as the surface failed under immense stress. Yet within these rings, the bright knobs still remain. These knobs are believed to be the worn-down remnants of ancient crater rims, slowly degraded over time by micrometeor impacts or the gradual sublimation of ice. Their brightness comes from the fact that debris has slid down their slopes, exposing cleaner ice at the peaks. Even smaller craters on Callisto reveal something unusual. Compared to similar craters on our moon, they are noticeably shallower. For example, one large impact structure spans well over 100 kilometers across, but is only a few hundred meters deep. This could be because the impacting object broke apart before hitting the surface, spreading the force across a wider area, or because later geological processes subtly smoothed the terrain. Despite being over 1 billion years old, many of these craters still retain visible ejecta patterns, showing just how little Callisto's surface has changed over time. Some craters display even stranger features. Instead of having a central peak like most large impact sites, certain craters have depressions at their centers. This unusual structure may be due to the nature of Callisto's crust, which is both brittle and relatively thin, possibly sitting above softer ice or even a hidden ocean layer beneath. Estimates suggest this crust could be tens to over 100 kilometers thick. Data from the Galileo spacecraft revealed that Jupiter's magnetic field does not fully penetrate Callisto, implying the presence of a conductive layer beneath the surface. This suggests that at least part of the ice layer may be partially melted or structured in a way that allows electrical conduction. There is also evidence pointing to a small rocky core at the center, raising the question of whether Callisto could support life in any form. For life as we understand it, 3 key ingredients are needed: liquid water, energy, and essential chemicals. Callisto may have water beneath its surface, but it lies far from the sun and receives very little heat. Without strong tidal forces like those affecting Europa, Its only internal heat source would be radioactive decay, which may not be enough to sustain active processes. Unlike Europa or Enceladus, Callisto does not appear to have plumes or vents that bring subsurface material to the surface. This means that to study its ocean directly, we would need to penetrate its thick icy crust, a far more difficult challenge. Because of these limitations, scientists generally consider Callisto less likely to support life compared to other icy moons. And yet, Callisto should not be overlooked. Its position, far from Jupiter, places it outside the planet's most intense radiation zones, making it a far safer environment for future human exploration. With abundant water ice that could be converted into fuel and breathable oxygen, along with a stable surface free from major geological activity, Callisto could serve as an ideal base for missions deeper into the outer solar system. Its low gravity would make launching spacecraft easier, and passing close to Jupiter could provide powerful gravitational assists for journeys even farther out. While this remains a vision of the future, it is not beyond possibility if humanity continues to expand its presence in space. Although the Galileo mission provided valuable insights, many questions about Callisto remain unanswered. Future missions, such as the European Space Agency's Jupiter Icy Moons Explorer, aim to explore this distant world in greater detail, performing close flybys and gathering data that may reveal whether a hidden ocean truly exists and what secrets it may hold. And, perhaps most importantly, what we have yet to discover. Because every time we think we understand a world like Callisto, it reminds us that the solar system is still full of mysteries waiting patiently in the dark, just beyond our reach. And now, turning our attention to Jupiter itself. On the 5th of July 2016, the Juno spacecraft entered a polar orbit around the giant planet. Since then, it has been gathering data from just a few thousand kilometers above the cloud tops, revealing a world more complex and more dynamic than we ever imagined. At its furthest point, Juno travels more than 8 million kilometers away from Jupiter, and each orbit takes about 53 days to complete. By the end of its primary mission in July 2018, it was planned to complete 12 orbits. At the time of observation, Juno had already completed its 6th close approach, placing it roughly halfway through the mission. And because the spacecraft remained in good health, the possibility of extending the mission became very real. One of the reasons Juno flies so close to Jupiter is to avoid the planet's most intense radiation belts. There exists a narrow region between the atmosphere and the main radiation zone, and Juno carefully passes through this gap. There had been concerns that even brief exposure would damage the spacecraft, but the radiation levels encountered were actually about 10 times lower than expected, greatly improving the chances of long-term operation. This was a critical improvement over the earlier Galileo mission, which suffered significant damage as it repeatedly passed through Jupiter's harsh radiation environment. By contrast, Juno's carefully designed orbit allows it to survive longer while still collecting high-resolution data, and the reward for that risk has been extraordinary. For the first time, we have seen Jupiter's poles in stunning detail. Instead of the familiar banded appearance, the poles are dominated by massive cyclones, tightly packed and swirling in complex patterns. These images were so unexpected that some scientists said they would not have recognized the planet at all. What we are seeing is a completely different face of Jupiter, one that had been hidden from us until now. Juno is also able to peer deep beneath the cloud tops using a microwave radiometer. This instrument revealed something surprising: a concentrated band of ammonia around the equator, extending hundreds of kilometers below the visible clouds. Scientists had but instead, it shows a complex and uneven structure, revealing just how dynamic and unpredictable the planet truly is. The data has also challenged our understanding of Jupiter's core. Previously, it was thought to be solid, but measurements of the planet's gravity suggest something far more diffuse. A core that may be partially dissolved or even absent in the traditional sense. This raises fundamental questions about how gas giants form and evolve over time. Jupiter's magnetic field has proven just as surprising. In some regions it is far stronger than expected, while in others it is weaker, creating an irregular and patchy structure. This suggests that the magnetic field may not originate deep within a solid core, but instead in layers of metallic hydrogen closer to the surface. This magnetic activity gives rise to powerful auroras, and Juno has provided the most detailed views of them ever recorded. These glowing displays are shaped not only by Jupiter itself, but also by its moons. One moving point of light, for example, is linked to Io, leaving a trail that marks its motion through the magnetic field. The colors and patterns reveal interactions between charged particles, the atmosphere, and the planet's immense energy systems. Most of Juno's data collection happens during just a few intense hours in each orbit as it rapidly sweeps past the planet. During these moments, every instrument gathers as much information as possible, capturing both scientific measurements and breathtaking imagery. As Juno approaches Jupiter, we see storms swirling near the poles, then gradually shifting toward the mid-latitudes, revealing the familiar yet intricate cloud patterns. Looking closer, small bright specks become visible within the atmosphere. These are not small at all, but massive clouds of water or ammonia ice rising above the surrounding layers. Some of them span more than 50 kilometers across, yet appear tiny only because of Jupiter's immense scale. At these altitudes, temperatures are so low that these clouds may even produce snowfall within the planet's atmosphere. Despite decades of observation, Juno has shown us that we are still only beginning to understand Jupiter. What we once thought was a well-understood planet has revealed itself to be far more complex, filled with structures, dynamics, and mysteries we did not expect. Years after its arrival, Juno continues to operate in good condition, having completed more than 20 polar orbits out of its planned total. Its orbit brings it within just a few thousand kilometers of the cloud tops, avoiding most of the radiation but still exposing it to enough that its lifespan remains limited. And yet, even within that limited time, it has already transformed our understanding of the largest planet in the solar system. It has shown us that Jupiter is not a static giant, but a dynamic, evolving world, one that still holds secrets deep within its clouds. Its magnetic field, and its hidden interior, and, perhaps most importantly, it reminds us that even in our own cosmic neighborhood, there are still questions we have not yet learned how to ask. The plasma torus around Jupiter is largely fed by the volcanic activity of its moon Io, which continuously blasts particles into space. To understand just how active Io is, spacecraft observations have captured massive eruptions, with volcanoes sending plumes hundreds of kilometers above the surface. Infrared measurements have also revealed intense hotspots, marking regions of ongoing volcanic activity. In fact, Io releases roughly 1 ton of material into orbit around Jupiter every single second. As Io moves through this plasma environment and interacts with Jupiter's powerful magnetosphere, it creates what is known as a flux tube, and jaryan of electric current traveling along magnetic field lines between the moon and the planet. This connection is incredibly powerful, capable of generating hundreds of thousands of volts and currents reaching into the millions of amps. During one of its close passes, Juno flew directly through this region and was able to take precise measurements, despite the immense energy involved. The spacecraft remained unharmed because the structure is spread over a large area and Juno passed through it in only a matter of seconds. Juno itself is an enormous spacecraft, stretching about 20 meters across. It has to be this large because it relies on solar power while operating so far from the Sun, receiving only a tiny fraction of the sunlight available near Earth. Even with its large solar panels, it can generate just over a few hundred watts of power. Its spinning design, which may resemble a simple rotating object, actually serves an important purpose, allowing its instruments to scan fields and particles in all directions more effectively. One of its key instruments is the magnetometer, mounted at the end of a solar panel to minimize interference. Using this instrument, Juno has created the most detailed map of Jupiter's magnetic field ever produced. While the field does resemble a dipole like Earth's, it is not neatly aligned with the planet's rotation. Instead, it shows irregularities, including a region known as the Great Blue Spot, where the magnetic field is unusually strong. By comparing Juno's data with earlier missions, scientists have discovered that Jupiter's magnetic field slowly changes over time, a phenomenon known as secular variation. This suggests that the processes generating the field are dynamic and evolving, likely driven by motion deep within the planet. Jupiter's magnetic environment also produces the most powerful auroras in the solar system, releasing enormous amounts of energy. Like Earth, these auroras appear near the poles, but they are far more intense and are mainly visible in ultraviolet light. Unlike Earth's auroras, which are largely powered by direct electric currents, Jupiter's seem to be driven significantly by alternating currents, possibly generated by turbulence in its complex magnetic field. The structure of these auroras varies between the poles. At the North Pole, they appear chaotic, forming filaments and flares, while at the South Pole they are more stable and circular. Bright spots within these displays mark where flux tubes from moons like Io connect to Jupiter, while fainter features correspond to interactions with other moons such as Europa and Ganymede. Understanding Jupiter's magnetic field is key to one of Juno's main goals: uncovering the structure of the planet's interior. The data collected has already challenged long-standing theories. Instead of having a clearly defined solid core, Jupiter appears to have a much more diffuse interior. Its atmosphere extends thousands of kilometers deep, transitioning into a vast region of metallic hydrogen that may stretch all the way to the center. Under the immense pressure inside Jupiter, hydrogen no longer behaves like a normal gas. Its electrons become free to move, turning it into an electrically conductive substance. This is likely what powers Jupiter's magnetic field, rather than a dense metallic core like Earth's. The planet's rapid rotation, with a day lasting only about 10 hours, further drives these internal motions, strengthening the magnetic dynamo. Looking at Jupiter's visible surface, we see bands of clouds moving in opposite directions at different speeds. These patterns are shaped by powerful jet streams, similar in concept to those on Earth, but far more extreme. The colors of these bands tell a deeper story. Bright white clouds are likely freshly formed, rising from deeper layers, while reddish regions have been altered by prolonged exposure to sunlight and chemical reactions in the atmosphere. Closer to the poles, the colors shift toward blue, possibly due to differences in sunlight exposure and atmospheric composition. Within these regions, smaller cloud structures can be seen forming, which may act as the seeds for massive storms. Juno has detected lightning within Jupiter's atmosphere, with storms appearing more frequently near the poles than at the equator, though the reason for this distribution remains unclear. Among all of Jupiter's features, the Great Red Spot stands out as one of the most iconic. Juno has revealed that this vast storm extends far deeper into the atmosphere than previously thought. While earlier observations showed it rising high above the cloud tops, Juno's instruments indicate that it penetrates hundreds of kilometers below the visible surface. It is also cooler than its surroundings in the upper layers, though its deeper structure remains an area of ongoing study. And as Juno continues to orbit this giant world, each pass reveals something new, reminding us that even the most familiar planet in our sky still holds layers of mystery waiting to be uncovered. At deeper levels, however, the Great Red Spot actually becomes warmer than the surrounding atmosphere. And this internal heat may be what helps sustain the storm over such long periods of time. It has often been theorized that the Great Red Spot is a permanent feature, but in reality we have only been observing it for about 400 years, which is nothing more than a brief moment on astronomical timescales. Looking toward the poles, other large-scale features begin to emerge. Unlike Saturn, which has a distinct hexagon at one pole and a single vortex at the other, Jupiter displays a far more complex arrangement. Around the South Pole, 5 massive cyclones form a stable pattern, while the North Pole is surrounded by 8. It is still unclear how long these structures can persist, but during the years of observation so far, they have remained remarkably consistent. Beneath the visible ammonia cloud layer, scientists believe there may be a deeper layer composed of water ice clouds. Although this has not yet been directly confirmed, detecting this hidden layer remains one of the key scientific goals. Using microwave instruments, observations attempt to identify regions where water may exist by tracking how Jupiter emits and absorbs radiation. Denser clouds block heat in infrared wavelengths, while potential water clouds may absorb microwaves, leaving subtle signatures behind. Jupiter itself generates heat from within, and this internal energy plays a major role in shaping its atmosphere. As more data continues to be analyzed, our understanding of this giant world is slowly evolving, revealing a system far more dynamic than once imagined. Years after its arrival, the spacecraft entered an extended mission phase, expanding its objectives beyond Jupiter itself to include close flybys of its icy moons. It had been decades since these worlds were last explored in detail, and new observations are beginning to reveal changes, activity, and hidden structures beneath their frozen surfaces. Equipped with advanced imaging systems, the mission has captured some of the most detailed views ever obtained of these distant moons, offering new insights into their internal composition and the possibility of subsurface oceans. The journey began in August 2011, and after traveling for years across billions of kilometers, the spacecraft entered orbit around Jupiter in July 2016. Following the completion of its primary objectives, the mission was extended, allowing for dozens of additional orbits and close encounters. When the mission finally comes to an end, the spacecraft will be guided into Jupiter's atmosphere, where it will burn up completely. This is done to ensure that no contamination reaches nearby moons, especially those that may harbor environments suitable for life. And in that final descent, after years of exploration, it will disappear into the very world it helped us understand, leaving behind a deeper awareness of how complex and how mysterious our cosmic neighborhood truly is. So on the 7th of June, 2021, Juno performed a close flyby of Ganymede, using the moon's gravity to adjust its orbit, shortening its period from 53 days down to 43. While a previous flyby in 2019 brought the spacecraft to within 97,000 kilometers, this time it came astonishingly close, just 1,000 kilometers above the surface. The images captured during this pass revealed nearly half of Ganymede's surface in remarkable detail, with a resolution of about 1 kilometer per pixel. The icy world appears textured and alive, covered in craters, contrasting light and dark regions, and long, sweeping striations that stretch across its surface. The darker regions represent older terrain, heavily cratered and largely unchanged for billions of years, while the lighter areas are younger, shaped by more recent geological activity. Those long striations, cutting across the Moon, are believed to be the result of tectonic forces, possibly driven by heat from a deep iron-nickel core hidden beneath the ice. Beneath that frozen crust, scientists believe there is a vast subsurface ocean of salty water, raising the possibility that Ganymede could host conditions suitable for life. But much about this hidden ocean remains uncertain, and the surface features we see may only hint at the processes unfolding far below. Another image from the same flyby reveals the bright Tros crater, its reflective appearance caused by fresh ice deposits, and perhaps even more striking is the view of Ganymede's dark side, captured in extremely low light conditions using a navigation camera designed to track stars. Even in near darkness, the level of detail is extraordinary. Craters overlap one another, ridges stretch across the terrain, and the surface tells a story of constant change over immense spans of time. One of the most surprising discoveries, however, did not come directly from the spacecraft, but from observations made alongside it. By studying ultraviolet signals, scientists had expected to find significant amounts of oxygen in Ganymede's thin atmosphere. Instead, what they found was something entirely different: water vapor. This unexpected result forced a major revision of existing models and suggested that similar icy worlds throughout the solar system may also release water vapor into their atmospheres under the right conditions. After Ganymede, the mission continued toward Europa, performing a close flyby on the 29th of September, 2022. Passing just a few hundred kilometers above the surface, the spacecraft captured dramatic images of a world marked by fractures, ridges, and deep shadows. Along the boundary between day and night, the surface appears almost three-dimensional, with long ridges and deep troughs casting sharp contrasts across the icy terrain. Like Ganymede, Europa is believed to contain a vast ocean beneath its surface. But new evidence suggests the story may be more complex than once thought. A closer image reveals a heavily fractured region, crisscrossed with ice ridges and grooves. Near the center, a dark patch stands out, hinting at activity beneath the surface. Scientists believe this may be evidence of material rising from below, pushing through the thick ice shell. Traditionally, it was thought that Europa's ocean lay deep beneath a rigid crust more than 10 kilometers thick. But new theories suggest that pockets of salty liquid, known as brine reservoirs, may exist much closer to the surface. These reservoirs could expand, deform the surrounding ice, and occasionally break through, creating surface features like the ones observed. It is a compelling idea, one that may reshape how we understand icy worlds. While these moons reveal their secrets, Jupiter itself continues to surprise. Decades ago, spacecraft detected flashes within its atmosphere, believed to be lightning occurring deep below the clouds. But recent observations have challenged that assumption. Instead of forming deep within the atmosphere, these flashes appear at much higher altitudes, in regions far colder than expected. At temperatures below -88 degrees Celsius, something unusual is happening. These storms are driven not just by water, but by ammonia mixed with water, forming a kind of antifreeze solution that remains liquid in extreme cold. Within these clouds, powerful lightning forms, and instead of rain as we know it, Jupiter produces something far stranger: massive hailstones made of ammonia and water slush. These so-called mush balls fall through the atmosphere, redistributing material and reshaping the chemistry of the planet in ways we are only beginning to understand. The more we observe Jupiter, the more it defies expectations. What once seemed like a familiar gas giant has revealed itself to be a world of complex physics, hidden oceans, and alien weather unlike anything found on Earth. And as the mission continues, each new pass brings another piece of the puzzle, quietly expanding our understanding of the largest planet in our solar system and perhaps of giant worlds far beyond it.